This will be a quick video just to introduce sort of the concepts of CFD, sort of the workflow, if you will, and some of the main considerations. Not any of the button clicks like some of the other tutorials, but more so the idea. First, here's an overview of the process, and I'll just say a little bit about each of these things. The first step, and perhaps even the most intensive, has nothing to do with the software, but really defining the problem. And this is where you as the aerodynamicist really need to understand what you're after. So you have to spend some time thinking about what's the goal out of this analysis. You know, what type of governing equations are appropriate? Is viscosity really important? Do I need to include compressibility? Is this laminar turbulent? Do I need to somehow model transition? Is that critical? Can I assume it's fully turbulent? You know, this is going to define whether we're using the Euler equations or the incompressible Navier-Stokes, the Navier-Stokes, or whether we have to go to an LES, or whether we're going to try and use a transition model. Is there any symmetry, you know, or can we assume symmetry? What type of dimensionality is appropriate? Does this have to be 2D or 3D? Is there a symmetry plane or axisymmetric? Just so you know, by symmetry plane, for example, this would be common with, say, like an airplane. I got an airplane here, right? It's the airplane geometry itself is a horrible drawing of my airplane. Airplane geometry itself is generally going to be, it's going to be symmetric. Now, if my flow conditions are also symmetric, like if this is my domain and I'm looking at a side view, and this is my airplane here, and I only just have an angle of attack, then the left side and the right side are symmetric. So I don't actually want to model the entire thing. I can just model half of it, and then I can use a boundary condition that's called a symmetry plane, and it will save a lot of computational effort. Now, if I have a side slip, right, so the velocity is not just in this plane, but I've got like a sideways component, then it's no longer symmetric, and I can't do that. But I need to think about these things beforehand, right? Like, what type of symmetries do I have? Let's see. I have to think about the operating conditions, right? Like, what are the free stream speeds? Is this steady or unsteady? You know, is there, how am I going to model turbulence, angle of attack, and so on? And you think about the geometry and the fidelity. I guess this kind of relates more to the second. On the geometry, the challenge here is that I generally want, well, I do want the geometry to be at a finer resolution than my mesh, right? Because if it's not, let's say this is my geometry, like I'm actually trying to model this fuselage that comes in like this, but it's so coarse and I'm just zooming in way a lot that it looks like this as I zoom in on the points. Then no matter how small I make my fluid mesh, right, I got these tiny cells here, then I'm still going to be capturing this sort of faceted geometry. So no matter how good I do that, you know, I'm not going to make it more accurate. So I need it to look really smooth here. So I need a very highly defined geometry. But I need to ask myself, what features do I need, right? So if I'm thinking about the full airplane, you know, there's going to be all these probes, pitot probes, for example, and fairings and gaps and you know, all sorts of little geometry things. Do I need all of those? Are important, because the more I put, well, maybe I can model them in my CAD program, but on in my CFD software, I got to mesh all of those, and that's going to make things way more complicated, right? I got to get good resolution around all these things. If I don't care about some of these things, maybe I don't include it, right? Maybe I sharpen up some of the trailing edges because I'm less worried about that base drag. You know, am I really trying to get an accurate number for drag? Am I looking more at lift and pitching moments? Again, it depends on what I'm after is really going to drive the type of fidelity I need here. I also have to think about the domain. As I mentioned in kind of tutorial videos, you know, there are different types of shapes. Sometimes we use a circular shape. Sometimes it's like a bullet shape. Sometimes a rectangular shape. Those are some of the most common. And, you know, the best practice guide of the software using will kind of have some suggestions on whether it's subsonic or supersonic or whatever. But in all cases, we need the boundary to be far away, right? So if I'm modeling some geometry here, if my boundary is really close, then I have no idea what type of boundary condition to put, right? I can't put, for example, that this is a pressure outlet, that the pressure is going to atmosphere, or in this case of a rectangular one, right? If it's really small, my geometry is like this big, I can't just put the free stream here because it's not free stream. It's being modified by this geometry. So I need to make the boundaries pretty big. As a rule of thumb, like 5 to 10 body lengths away. And if you really want to be careful about this, you can do what's called the boundary placement study, which means you make your boundaries some certain size, and then we make them bigger and bigger until nothing is changing anymore. Then I know it's big enough, but it's a little complicated because I have to do it at the same time as I'm doing a mesh study. But as rules of thumb, again, we typically need more space downstream as compared to upstream because of the changes in the wake, and more space side to side as compared to upstream. But in all cases, again, usually the mesh is getting bigger and bigger, so it's not that hard or not that expensive to just go ahead and make the boundaries bigger, right? Like go to 10 times the body size and then you'll be safe. Because what happens is the mesh grows, as we've seen. So near the body, I'm just going to draw this horrible mesh, right? The mesh size needs to be super tiny because I got to resolve all these tiny features. I got to resolve the flow features really close. But the mesh cells are going to grow and grow. As they get far away, they're pretty big. And, maybe really far away, they're like the size of the body. So if I go from 5 to 10, maybe it adds, 5% or 10% to the number of cells. So not that much, but I've gotten safely away. So I'll typically go pretty far because it's not that expensive usually. Okay, so after I've figured that out, I then create a mesh. This is, I would say, of all the steps, probably the most challenging from a CFD expertise point of view, because your mesh is, well, everything drives everything, but the mesh is really critical to get right. And it's hard to know, like, did I put enough cells in this spot? Because if you didn't, it's not going to be accurate enough. So the mesh, I have some pictures here. Right? Here's some pictures of some meshes. These are some different types of mesh. But how do I know, right? Like, did I get enough resolution here? And so we'll do things like mesh refinement studies. Those are absolutely critical. You never want to show any results without doing a mesh refinement. And that means I take all my cells and I divide them. In the ideal case, right, this is totally impractical, but just to say, let me just draw this ridiculously coarse mesh because I don't want to spend all day drawing a mesh. I would take every cell and I would, divide it up. So in 3D, maybe I divide it into 8 things, or whatever. And I'm ignoring the geometry here just to make my life easy. I'm not meshing around it. That's totally impractical because that's going to balloon my cells very quickly. But what I do is I try to refine around areas of interest as much as I can. So sometimes we'll use something like, we'll define sort of the size I want around here in the far field relative to some reference area. In star CCM, is called a base size. And maybe I'll define things in the near body relative to some size that I want, and kind of a transition rate. So I can kind of tie everything into a number, and maybe I'll define kind of a size in my wake, for example, if I'm trying to resolve that. And I'll modify this. And this will be a good way to see convergence. So if I have, let's say, number of cells, and this is like, I don't know, let's say it's my lift, for example, I would like to see that this is going to flatten out, right? And if it's flattening out, that means that hopefully I've reached a mesh independent solution, that my mesh is not creating artificial error here, right? Because I'm too coarse. I've got it fine enough that, that I'm not introducing additional error, discretization error. Of course, that's imperfect. That means I've resolved things in the right spots, right? Just to give you a dumb example that, you wouldn't do, but let's say this was my mesh. And I did my mesh refinement study, and all I did was refine cells over in this area. And then I did it again in this area. Well, that would flatten out for sure. Nothing's changing, but I haven't refined everywhere. I've only refined in this tiny little corner. So that's going to be misleading. So this is not, this is necessary, but not sufficient, I guess is the way to say it. And the reason why I say this is really hard is because this is where your computational budget runs into a problem. We always, of course, want more cells, but that's the whole problem, is the more cells I make, the longer this takes. And we're always trying to solve harder problems, more complex geometry and unsteady and so on. So they already take a long time. And so if I just throw tons and tons of cells, it's just infeasible. So it's kind of the art of, I need to try to do this really efficiently, figure out where I'm going to have a lot of changes and really focus a lot of cells there. Other places where I can get away with bigger cells, and then do some mesh refinement studies off of that. But I can only go so far, right? And there are techniques, actually, things like Richardson extrapolation we'll talk about later, to where maybe I don't quite get here, but I can extrapolate and figure out where it's going. But yeah, this is the difficulty, right? Is creating a good mesh and doing those refinement studies. Okay, then I specified boundary conditions is relatively straightforward. I'll talk about a few of these later, but this is where I say, you know, this is a free stream, this is a symmetry plane, this is a pressure outlet or whatever. We initialize the flow field. Often we just initialize with uniform flow based on whatever my uniform velocity is. But the other way we would do it is if we're doing, this is a common technique, is where I might solve on a coarse mesh and then refine the mesh and resolve, and then refine the mesh and resolve. And sometimes that can help me get to a good solution where sometimes even faster, but at least if I'm having numerical difficulties, I can solve on the coarse mesh, and then that'll be a good solution for the finer mesh, and I can refine in some of these places where I may have had difficulties converging early. I've already gotten kind of close and I can refine. This is also, by the way, a good way to do that mesh refinement study. Since I should do that anyway, and you should always do that, since I should do that anyway, I can do this to kind of iteratively refine towards a solution, and it isn't too costly because I've already got a decent solution. So when I refine, running it again is pretty quick. Okay, once I'm done, I do the post process where we make a bunch of pretty pictures. We extract things that we're interested in, the forces, pressure distributions, and so on. I definitely need to do some VMV, which we'll talk about, and then I may repeat certain parts. Often we may find I need to improve the geometry. There's some features here I need to add, or I need to improve the mesh in this area, or I need to add some other part of my mesh. Like I need to add sort of a wake component of the mesh, or whatever. I need to change some of the parameters and do this again. Here are two sort of big categories of meshes. Most of the time you'll do things unstructured. Structured is very nice. The structured mesh is based on the geometry. You could think of it as like a generalization of just a Cartesian grid, but I can morph it around any sort of shape. This generally only works around relatively simple shapes, but it has very nice behavior. And we will use structured meshes still, but we'll use them only in the near body. So kind of in the boundary layer, we'll use a structured mesh. We'll call it Prism Layer, but it's a structured mesh in the near field. It's hard to do in general because, you know, as I have complex geometries, think of an airplane with wings and tails and winglets and maybe landing gear and other things. I can do some nice things around the body, right? Let's say I've got these multiple bodies. I've got a body here, and let's just draw a tail here, whatever. And I can create, nearby, I kind of know the kind of shape I want to create this nice structured grid. But over here, I can do that too. But what happens as in this in-between area, right? It's not going to be so nice. And so an unstructured grid doesn't rely on the structure. And they're very general methods I can mesh around arbitrarily complex bodies. So this is kind of the most common technique, is that we use a structured one near body. There are reasons for this. As we talk about later in the semester, viscous flow, we find that things change very quickly normal to surface, but very slowly along the surface. So we want cells that are kind of skewed there, but they have to be in the direction of the body, right? So that we're capturing that normal velocity. So we want near the body what we call prism layers, but to handle kind of the more general complex geometries, we'll generally have an unstructured mesh. Things to look for in a mesh, except for like this exception I mentioned, the boundary layer, and I'll just draw this in 2D. We generally don't want cells that are really skewed. We want things that are isotropic, right? Unless, again, the boundary layer is an exception because we know things change very quickly in this direction and very slowly in this direction. So I can get away with these stretched cells. But everywhere else in some arbitrary point of the flow, I don't generally want these skewed cells, or if it's like a triangle or something, if it looks something like this, it's going to have some numerically poor behavior sometimes if these get too stretched. I want things that are closer to isotropic. I also don't want things that stretch too quickly. So if I've got, you know, this row of tiny cells, and then next to it, I've got these huge cells, well, I basically have lost all the information as I go from this cell to this cell. Because I went to this really fine resolution, I resolved velocities and pressures in these ones, and suddenly I have to somehow average all of that behavior into like one velocity on this face here. So I'm losing a lot of things. So I want my cells to grow gradually. As a rule of thumb, I would say maybe grow at about 20% one stage to the next, right? So you notice here, there's kind of a gradual progression, same here, right? So I want to grow these out. I should say maybe a word about how these are solved, why we have a mesh. So the idea of a mesh is that we have these governing equations, right? The Navier-Stokes equations, for example, and these are complicated equations. I can't just solve them for some arbitrary geometry, but what I can solve them is for this tiny little box, right? I can, let's think about it in 2D. I can solve it over this rectangle or this triangle or whatever in 2D. It's a simple shape. I can do that. And so there are two ways to do that. I'm going to do the rectangle way because this can be maybe easier to visualize. So I've got this mesh here. I've got some governing equations, and let me just write the 2D mass equation. So let's just say d rho u dx plus d rho v dy equals 0. Well, one approach is what we call finite difference, and that is I'm just going to have, let's call this I, and this will be I plus 1 and I minus 1. And this would be, well, actually, let's say this is ij. We'll give it a coordinate. And so this would be ij minus 1. And then this one up here is running out of room. Sorry, this is ij plus 1. Just give it some names, like it's kind of like a matrix. At every point on my cell, I have, let's say, a pressure, a density, a velocity, and I can just discretize this equation. So in this case, I could do something like rho u, and I'm just going to group them as if they're one variable here, at I plus 1 minus rho u at I divided by x at I plus 1 minus x at I. That would be an approximation for this derivative here, right? And so on to here. So I basically take my equations, I make them into this discretized form, and then I basically have this huge linear system of equations that I can solve. And they won't be right because, you know, they're based on my prediction for the value here is based on the one here, but that one's not right either. But I get an update, right? And so then I can do it again, and I do it again, and I do it again, and I do it again until I get a converged solution. And they're driven by, like, for example, let's say I have a free stream. I have some known velocities here, way upstream, and they're kind of being fed through here, right, across the domain and across, say, I've got a body over here, and I have to get the right boundary condition there. So basically, my boundary conditions are driving the solution, and eventually that will all converge. So this is called a finite difference approach. Another approach called finite volume is I could have, say, the same kind of domain. And instead of thinking about putting things in the cells or on the nodes, I could think about the cells. So I could say, well, here's a cell, and I could think about it like a control volume. There's some velocity coming in, some control volume going out. We've done this a bunch of times where we did a little integral momentum approach. So the first one is like a differential approach. This is more like an integral approach. We call this finite volume. So I could look at the fluxes of momentum and mass coming in. I just use these same equations. So I'd have like some rho u coming in, a different rho u coming out, and I just apply the equations on this little tiny volume. And again, I apply that on every tiny little volume. They're all related through this big, huge linear system equations I solve and iterate, blah, blah, blah. So those are the two most common for CFD: finite difference, finite volume. Finite element is another approach that can be used. I'm not going to really discuss it here. It's more common in structures, but it is used sometimes in fluids. And yeah, for interest time, I'm not going to get into that. Okay, so that's kind of meshing. Let's talk about boundary conditions. And these are kind of the general ones you'll see. There are more specific ones, and I'm using the names from Star CCM, but your package will have different names, but mean the same kind of thing. So one for incompressible flows is what we call velocity inlet. It's an incompressible flow, so all I need to specify is a velocity. If I'm going to compressible flow, then velocity is insufficient, so I would specify like a Mach number, a pressure, and a temperature. But in both cases, what these mean is that I've got, and typically this would be like, you know, either a bullet or like a rectangular shape. I'd be specifying things upstream, right? And I've got some body here. Pressure outlet, this would be like in this rectangle case, like these sides here. I'd be specifying that the pressure is at atmospheric pressure, right? There's no change in pressure. So I'm assuming that these are far away. So that's again why I need boundaries to be far away. So this just tells my CFD solver this is what's driving the solution. Impose a pressure, right? It's going to say p equals p infinity here, for example, and here, and v equals v infinity here. And then it's just going to let that drive the solution. I'm going to use my finite difference or finite volume solution. And then I'd have another condition here, which is like, say, a wall, which says the normal component of the velocity has to be 0, for example. Or if it's no slip, then v at the wall is 0, right? So those are the two different kinds, whether it's inviscid or viscous. So once I specify all these boundary conditions, then I just iterate until this solves. So we've talked about the velocity ones, pressure, wall. I mentioned the symmetry plane earlier. Another one is axis. That's so if you've got like a axis symmetric. So imagine I've got this line here and I can rotate things around the axis, something like a propeller or inside a jet engine or something like that, where I'm just modeling something that's 2D axisymmetric and I can model just one section of it. This is common in like a turbo machinery analysis. Okay, so we talked about how this is an iterative thing. So one thing you want to monitor or look at is these residuals. Residual means, let's say I have my mass equation. I'll just write it again, d rho u dx. I'm just saying 2D here. D rho v dy equals 0. My residual is, I have these governing equations, and at any given iteration, they're not right? So initially, I created this thing, I set my boundary conditions, and I put the free stream everywhere. And when I go to solve this, these equations are not going to be correct everywhere. So what I get is a residual, and the residual is I take everything and I set it equal to 0, and whatever, if I plug things in and I calculate this, I'll get some number and it won't be 0. So I can just plot that, and over time, it should converge towards something that is 0. On a computer, right, we never get to 0. I'm just going to drop many orders of magnitude. And so I should see this drop towards a very small number and flatten out. So over time, this will converge. And the reason why I have many is that I have many equations. So if it's incompressible, I've got mass and 3 momentum equations. So that's 4, and that's what these are. This is the mass, 3 momentum. So this must be an incompressible Navier-Stokes. I know that because these are turbulence model ones. So if we add a turbulence model, that adds 2 more equations, or it depends on the turbulence model. This is a 2-equation turbulence model. We'll talk about this much later. There's a K omega turbulence model, so it adds some additional equations that I need to converge. If I had a compressible flow, then I'd have another one here. It could be pressure, temperature. These are related, so it just depends which one they show. But I basically want all these residuals to flatten out. But I would also look at not just these residuals, but I would plot the things that I care about. So say I cared about lift, I would plot that and make sure that that is also, leveling out. Drag, if I care about that, right, I would plot that as well. If there's a pitching moment that I want, I would plot that and make sure that these are flattening out. And typically, lift is going to be much easier. It will converge much quicker. Drag, I may need to get a much finer mesh to resolve that, again, specifically for streamline shapes, which we usually have in aerodynamics, because the projected area in the drag direction is so small, you need a very fine mesh to get a good solution, because you're just integrating around the shape, integrating pressures and shear stresses if it's viscous. Okay, last thing, super important step, verification and validation. A great convergence is start, but that's not really a verification. The difference between verification and validation is verification is this accurate compared to the governing equation? So in other words, am I solving the other equations correctly? You don't have to do this for CFD per se, because you didn't write the software. Well, you would if you wrote the software. You didn't write it. Presumably it's been verified. But the idea would be, as you're writing software, if we're writing a potential flow solver, did I solve it correctly? I compare it to another potential flow solution, a known solution. Did I get the correct answer? Validation is, how does this match reality, right? So I may have solved it correctly for potential flow, but it may be that potential flow is a poor approximation of reality for the situation I'm in, because there's separation or it's compressible. So both of these things are important. Sometimes people want to skip just a validation, and that's always important, right? I want to compare it to experiments. But if I only jump right to validation, the problem is that it'll always not exactly agree, right? Because of course it's an experiment and it has its own source of error, and my simulation is not going to be perfect either. So when there are inevitably errors, I have no idea if those errors are just because of, I'm trying to match reality, or if there's errors in my implementation. So this is kind of a two-step. I want to do verification, make sure I'm actually solving the equations correctly. Again, we don't necessarily have to do this for CFD directly, but you know, if I'm doing a potential flow solver or whatever solver, I'm writing CFD, I need to do that. Then I do validation because I know I solve things correctly. Now, how well does this match reality? Yeah, so for verification, I guess in a CFD sense, I would consider it at least doing the grid convergence study. If you have time or an unsteady simulation, you also have to do like a temporal convergence, maybe a boundary. The only time we do boundary refinement is if you're trying to be aggressive and shrink your boundaries because you're really doing a huge simulation, but typically we just make them really big. I guess another way we could do verification, I shouldn't say we don't do verification on CFD, because while you know the equations are being solved correctly, you don't know that you actually have put in the geometry properly and done the right boundary conditions. So here's an example. Let's say I have a solution for the induced drag of a wing from a textbook, and it's kind of an analytic solution. That would be verification, right? So I take my wing, I know what the solution should be analytically, and I'm making sure I get that. And I want to do that, right? That just helps me know that I set things up properly, that I use the right boundary conditions and so on. So I take back what I said, verification is still important. But then once I compare that drag that I compute to experiments, that's validation, and both are important. I want to make sure I'm doing both. And typically what will happen is we start with a simple example like a wing to where I have a known solution. I do verification. I make sure I'm doing everything properly. And then I change the geometry a little bit to the thing I care about that I don't have a solution for, but it's basically all the same process. And now I have a little more confidence that my verification is correct. And now I can do validation against the case that I'm interested in. All right. That's it for this introduction. We'll be talking about CFD and different contexts a little more. We'll get into some of these more details later throughout the semester.